My name is François Diaz-Maurin. I am a nuclear security visiting scholar at the Center for International Security and Cooperation, CSAC, here at Stanford. This is actually my first presentation here at Stanford. I spent the last 7 years in Barcelona, where we were trying to introduce concepts from complexity theory to sustainability assessment. So it's what I will be sharing with you today and presenting what we were developing there. So whenever we start discussing sustainability, we come up with asking ourselves some questions about sustainability of what, for whom, and for how long. But today I will be focusing on how do we assess sustainability. There have been some efforts in trying to come up with methods. And one example of what we have been working on is a multi-scale integrated assessment approach, which basically looks at society as a metabolic system based on various sectors. So if you wish, you have households, service and governments, building and manufacturing, agriculture and fisheries, energy and mining, and so on. And those are like organs in a body. They provide some functions, whether they provide food, they provide energy, and they have some requirements in terms of land use, energy flows, population or labor, human activity, if you wish. And how it basically works like this, it is an hypothetical example here, in which you have the whole society is having various requirements of flows, so it can be food, energy, water as well, and funds, which are basically those things that we consider constant over the time horizon of the analysis, mainly speaking the population and the land. And all those are expressing describing patterns of the society in two senses. Vertically speaking, the sum of the parts make a limit, a boundary to the system. For instance, land that is allocated to agricultural activity is no longer available for energy. And it's relevant whenever we discuss about energy transitions with renewable, etc., that need lands. Another forced relations we have is horizontally. We can also have flow fund indicators. Flow fund indicators are mainly metabolic rates, which are flows over funds. It gives us the ability to describe a society in its forced relations, in its pattern. So we can actually, and we have compared, for instance, European countries and other countries, and generally speaking, you get pretty much the same kind of numbers in terms of how much energy do they use per hour. And this differs, of course, to the various subsectors you are looking at. So you have more intensive sectors than others, etc. So having this in mind, we can move to where it's coming from and how complexity is introduced into this kind of approach. So when dealing with the sustainability assessment, you really rapidly reach a problem that is called nowadays a nexus, which is basically a tension between energy security, food security, and water security. It's much broader than that, but this got a lot of popularity recently, in recent years. But the problem with that is that it tended to become a buzzword, basically. It has, in an editorial nature, made really a case against this kind of nexus approaches, and saying basically this kind of word were already around in the 19th century. So there is no so much something new. This was used already to explain the functioning of the brain, for instance. But and it's my main point today, I think, and we have shown that the nexus ceased to become, to be a buzzword whenever we try to introduce complexity into it. And I will use as an example the first field in which we introduced complexity, which is energy analysis. So the introduction of complexity in energy analysis has followed several steps. The first one is with the birth of energetics. For those not familiar with it, is basically the science of energy. It was developed in the 19th century with people going through the scientific revolution by development of the classical thermodynamics, equilibrium thermodynamics. And then thereafter, they had their own energetics had its own revolution in itself with the development of non-equilibrium thermodynamics in the 60s. However, those two fields were not sufficient to make energy analysis credible as a field and responding to the needs of society and providing understanding on how society is using energy. And there are historical reasons for that. First, the classical formulation of energetics through equilibrium thermodynamics was having mismatch between huge claims and the ability to actually use it. It was mainly based on ideal cycles that engineers were envisioned in the lab, but those were not the reality observed. So there was also an unrealistic scope trying to explain the society through this narrow look at energy. And the second problem from non-equilibrium formulation of thermodynamics, it resulted this new paradigm in new theoretical approach to energy, but it failed to provide practical operationalization of those concepts. So as a result, energy analysis was really unable to answer questions and to explain, for instance, why the energy crisis happened in the 70s and the 80s. So there was a need for a second revolution in energetics, which has been mainly based on two principles. So first is about there is no single definition of what energy is. It's 1 joule of electricity is not 1 joule of fuel, although those can be expressed in joules, they don't represent the same thing because they are not used in the same way. A second important principle introduced is about the importance of making an assessment across scales. So the introduction of complexity has been going first by doing a critical appraisal of the existing energy analysis at the time, mainly based on hierarchy theory, which is a subfield of complexity theory. And in it, this critical appraisal identified some shortcomings of methodological shortcomings of energy analysis, the truncation problem. So how do you define your boundaries, especially whenever a system is linked to the external world as well. Also the problem of aggregation of different energy forms, how do we formalize it? And the joint production dilemma for those systems that are producing many different things. Thinking of a mine, for instance, you can get uranium and other products out of the same mine. How do you account for the requirement of that mine, for instance? But at the same time, there was an underlying complexity in energy analysis already going in parallel, just like in the natural world, as Professor Riskin was referring to earlier this afternoon. Complexity was, for instance, already at play with the explanation of Ostwald. So Wilhelm Ostwald, a professor of physical chemistry, he was, as a matter of fact, a winner of Nobel Prize in chemistry. And after winning this Nobel Prize, he got obsessed with this importance of trying to explain the importance or the use, the role of energy in society, and developing a real scientific field called energetics. And he was calling that the energetic imperative. And he was already describing society as a metabolical functional body having various organs that maximize their energy use. And it's actually what we are looking at. Whenever we try to make more efficient production sectors, but in order to be able thereafter to diversify our economy and having more services, more institutions that stabilize the society and provide diversifying activities. So this led thereafter to the complex formulation of energetics. This was done through an integration of concepts mainly coming from various fields linked to complexity theory, from non-equilibrium thermodynamics, from complexity theory as well, and from other fields such as even linguistics with Chomsky's work on the generative grammar, and from theoretical ecology and bioeconomics with Georgescu-Roegen's font flow scheme, which I was referring to earlier. So with all those concepts, they were translated later in alternative analytical tools. I will show you 4 of them here. The first one is the multi-purpose grammar, which is basically a presentation of semantic categories of a system. Here it's an example what I did on energy systems, describing the various types of energy. So whenever we are talking primary energy sources, it is a form of energy. You can have also gross energy requirements. Because why they are different? One is expressed in biophysical terms, in tons of products, in gradients, natural gradients, etc. Those are already expressed in joule of primary energy. But you have also energy carriers that are directly used and end uses, which are the actual use of energy, various energy forms, fuel, electricity, and thermal energy in the various sectors horizontally. And those semantic categories are mapped, later formalized using formal categories. Why this distinction is important? Because it's semantically open. Any system is organized differently. You can have here a map of a society, which is a country, but sometimes we are just looking at a village, and a village does not necessarily have this complex organization of energy flows. So we adapt grammars to various systems, and it has been also applied to food systems, water systems as well. Another tool is impredicative loop analysis from Ulanovich, which is basically linking, for instance, energy to human activity, so a flow to a fund at the same scale, and we look at what is their metabolic rate at the total in the society of energy use per unit of human time. And we can look at lower levels, of course, the same use of energy over time. And with those indicators, we know forced relationships across scale. Then a similar tool is the use of dendrograms. Dendrogram basically is about splitting a flow or a fund across the same scales. So you get, for instance, the total energy throughput that is divided between households or paid work, and further split later on between paid work, between services and government institutions, if you want, and primary sectors, etc. And you do the same, for instance, with human activity. And for each one of those sublevels, you get metabolic rates, which basically, generally speaking, are really useful to compare countries between each other. A country that is really intensive in its use of energy per hour in the household is, generally speaking, a country that is more developed, able to use electricity at home, for instance. Even though this is really low compared to the production sectors, which per unit of hour invested in this sector are, of course, using a lot of energy to get this. And the last tool that we are using is a multi-level, multi-dimensional accounting scheme, which is basically trying in a table to represent. So for instance, here is the total energy system of a country having a requirement of human activity, requirement of thermal energy, requirement of installed capacity, and the same for mechanical energy, which is basically electricity here. And producing a certain amount of either thermal energy or mechanical energy. But this total here does not really exist. It is only the expression of subparts of the various sectors we have, and we can compare them looking at 3 main categories, if you want. Physical gradients, that are the local supply sources here. the imports that are imported as fuel for making electricity mainly, or the direct import of electricity or fuel already refined, for instance. But what is useful here is whenever you introduce a new system or you make a big change in this system in terms of, for instance, energy transitions, you are able to reflect those changes at a higher level, at the level of the energy system itself. And remembering the previous slide, we can ever infer to the overall societal metabolism what are the impacts of those changes. So really able to cope with a certain form of complexity here. And so all this is put together in sort of toolkit that we call integrated assessment in energy system in that case, in which we look at the inside view of the society, looking at all the requirements of production factors, and we are able to discuss the viability, whether the introduction of a new system is incompatible with the existing pattern of this society, for instance. Thereafter, we look at the benchmarks, so the metabolic rates across the various sectors, and how they are compatible with either expected values or the current values whenever we affect those metabolic rates by introducing a new system. So it's called desirability. And then the outside view, we look at the impact in terms of environmental loading, either by requiring resources or generating pollution or waste, and also the use of space, land, whenever it is available. And this gives us an idea whether or not a new scenario is feasible or not. And all those are related to each other, and in terms of negotiations between those three criteria of sustainability we are looking at. So this is formally called the Museism approach, which is a set of principles for the multi-scale integrated analysis of societal and ecosystem metabolism. This was developed by my colleagues already 7 years ago now, and it has been applied to many, many cases of various types of systems, agricultural system, household metabolism, energy system, whenever in all parts of the world. It's an accounting system and an approach that can be used, and it has been used in some cases, not always, within participatory frameworks in which the grammar and the semantic categories are actually given by the community we are dealing with, or the stakeholders if we look at national level. So it complements conventional dynamic models. It's static. We look at a snapshot in time or expected future pattern of the society. It's definitely not a model of dynamics in time, and it's not a way to generate deterministic or optimized simulation and predictions, because it's semantically open, and we are aware that there is a possibility of new emergent or reorganization of a society. This is why we would be critical of using this kind of tool to do scenarios over the next century, for instance. It will be a little bit difficult to do. So what it does, basically, it put together energy, food, and water at the moment, and look at also other factors such as population dynamics, greenhouse gas emissions, and also land use changes. And it works across scales. Can be applied at national level and looking at subnational levels, or it can be applied in a local community or a set of villages, for instance, in rural areas, and it is dealing then thereafter with their sub-unit levels there. And it's mainly, generally speaking, it's used first as a diagnosis in which we generate an accounting of how we describe how the society is organized at the moment. And we have thereafter the metabolic rates and indicators and allocation of flows across the scales. And thereafter, we can make some simulation, stress tests, scenarios, and so on. So it has some advantages and limitations, as a matter of fact. It is semantically open, as I was saying. It can be used within participatory frameworks. It is, we argue strongly, a remedy for reductionism, because we are not putting all all the numbers into thereafter one number of energy or content, for instance, we are forcing the analyst to look at various aspects that are not commensurable. And it gives quantitative coherence across scales, especially when using this kind of inferences and relationships across scales in these tables. So the limitations basically is only human can do it because it is tailored to a specific case. The semantics, there is a limitation to generalize this kind of tool to study all kind of systems. But it can still be some way standardized whenever, for instance, you compare similar countries, for instance, countries in Europe, and you compare them between each other, more or less they are using, and you are first at the same scale, and they are using more or less the same type of energy in the same way. But of course, you cannot really compare. When I was applying it to Namibia, I had to split between rural areas and urban areas just because they were totally differently organized in their relationships to land, energy, and other resources. And in the end, and to finish with this point, it requires really a commitment to holistic analysis and transdisciplinarity. We have been working with the FAO, the United Nations, and we developed a collective, we published a collective book on the Nexus, and we were actually all a bunch of so-called experts in every areas, and I was working on energy systems, and I was really arguing with the colleagues, but it's not working that way, etc. And actually, it was only possible because we had different mindsets, but we were forcing each other to work in a description that was consistent, quantitatively speaking. So why do we use numbers here? It's because we have at least the agreement that 1 + 1 = 2, but there, how do we develop the 1 is our own explanation. So it requires a separate analysis of the energy systems, a separate analysis of the water systems, and thereafter we come together in an agreement in which we know the implications at the societal level. So we were asked by the FAO to develop this through 3 case studies. I will not detail them here, just to mention, for instance, in the Republic of Mauritius, we were asked, they had a problem of overproduction of sugarcane. Mainly speaking because they used to sell sugarcane at a higher price through a specific mechanism to Europe, and Europe stopped to consider sugar as this labeled product, which was, mainly speaking, reducing their ability to sell at a good price sugar. So they were having a problem. But sugarcane, as some of you may know, is one of the plants that is getting a lot of nutrients out of the soil. So they have this environmental problem at the same time. So we were first trying to see what is the possibility of producing ethanol? And in the end, it turns out that it's not that clear that there is a real potential for that. So we came up as a sort of alternative scenario in which why not diversifying the use of crop cultivation in order to reinforce self-sufficiency? It would make even more sense, and they could even sell products to the tourists coming in the island, for instance. So this kind of scenarios. In Punjab, state of India, it was another story, which basically they are overdrafting water from the underground because they got subsidies for energy, for electricity. So, and in doing that, they reduce a lot the overdraft the water from the soil, and they do that because they have a strong tension. They are basically providing the grain, especially rice, for the rest of India. So basically, the Punjab state of India is acting as an organ within India. They don't even decide the price of the rice they are selling to the rest of India because it's a forced internal market. So they cannot go outside of India to sell it. So we were looking at the consequences of those trends. And in South Africa, we were mainly looking at the potential of 2 energy sources, CSP, concentrated solar power, and woody biomass for generating electricity production and looking at the impact on land mainly. So the ongoing applications, there are two main ones. In Europe, my former colleagues are working on a big European project now and applying this kind of framework, adding to it some narrative analysis on biofuel production, fracking, GMOs, tradable permit, and desalination. And here at CSAC, I'm working on nuclear waste management, and I just started, so it will be for the next 2 years. With this, I will stop here. Thanks.
Thank you very much, François. We have time for like a few questions about this talk, and then we'll have time for just a last closing few minutes just overall. So yeah.
Could you go back to the slide on the limitations
Yes.
of this approach? So how can, and this is really impressive. It brings a lot of things together that I think are really important. How can this, I'm not sure I understand why it can't be generalized and specialized to other kinds of complexity science, to other situations.
So if I understand well, why it cannot be generalized is a different story than why it cannot be used in different areas. It can definitely be used in any kind of system, but the model itself, if you want to call it a model, the approach, quantitatively speaking, will be looking at different categories. So the energy use, for instance, or the production of food will be done totally differently from one community to another or from one country to another, because they are organized in a different way. So for instance, you can have a country that has no so much diversification of its services just because they are not good enough in the production sector. Mm-hmm. Why? All our diversification in our modern societies have been possible because we have been making more efficient use of the resources that we are either importing or using, and thereafter we are able to have a standard of living that is providing, Václav Smil is explaining that basically we have an advantage. We are creating a gap between the basic requirements and what we are actually getting into our economy, and in between we develop a new use of energy. Still, this can be applied to any kind of system.
But what I was wondering is we've seen today that there are a lot of analogies that are used, a lot of analogies that are used in conventional science, neurons or agents, whatever. So energetics, this kind of revised energetics, could be used in a cultural analysis as analogy. I think it would be interesting to pursue it beyond the strict energetics application.
Yeah.